Hi there, Mr. Sutton here. I've got the AB Calculus 3-1 Extra Practice number 3 solutions for you on the power rule. For this problem, to make our life a little bit easier, I'm going to rewrite this with a negative exponent so I can use the power rule. So this is really 4x to the negative 10. And then using the power rule, this is going to be negative 40 x to the subtracting 1, so this is negative 11 power. On this problem, I'm going to rewrite this with a fractional exponent so I can use the power rule. So this is 4x to the 3 over 10 power. And then using the power rule, this is going to be 3 tenths times 4, so that's going to be 12 tenths or 6 fifths. And we'll have x to the, 3 tenths minus 1 is really minus 10 tenths. So that's negative 7 over 10 for the new exponent. For this problem, to take the derivative, I'm ultimately going to use the power rule. But first I need to rewrite all these with normal looking exponents. So this 6x to the 10 thirds is fine the way it is. But this next one, I want to change this to x to the 3/8 power. And for this one, I'm going to rewrite this as 4x to the negative 8. So now that I've got x to the some kind of constant power, I'm going to use my power rule. So we've got 10 thirds times 6. That's going to be, let's see here, this is really 6 divided by 3 times 10. So that's 20. So we've got 20. X to the, and I have to subtract 3 thirds, so 7 thirds. For this next one, we have 3/8. X to the, we'll have to subtract 8/8, so that's going to be negative 5/8. And this last one, this is going to be 32. X to the, negative 8 minus 1 is negative 9th power. On this one, we're trying to take the derivative of this expression. 5's derivative is just going to be 0, so we're not going to worry about writing that. But this next one we can use the power rule on. This is going to be negative 20 x to the negative third because we're subtracting 1 and making this more negative. For this problem, we're going to use the power rule to take the derivative. So going from left to right, let's see, 6x to the a. A is actually a constant, so we can use the power rule there. We know it's a constant because x is what we're taking f of over here. So I'm just going to use my power rule. We've got 6a. And then we'll have x to the a minus 1. We don't know what a is, so we can't really do more with it. We're just going to leave it there. Next one, this is going to be 27 x to the 8th. And then finally, 6 derivative is just going to be 0 because it's a constant. So we are done. To make my life a little bit easier on this problem, I'm first going to rewrite these with exponents. So we've got x to the 1/2 power minus 4x to the 1/3. And then this is going to be, plus 6 fifths x to the 1/4 power, negative 1/4, because we've got a reciprocal of a radical function. Now I'm going to use the power rule on each of these. So for this first one, this is going to be 1/2 x to the, 1/2 minus 2/2 is negative 1/2. For this next one, we have negative 4 thirds x to the, we have to subtract 3 thirds, so negative 2 thirds. And this last one, this is going to be negative, 6 over 20, which I can reduce to 3 over 10, so negative 3 tenths. X to the, we have to subtract 4 fourths, so this is going to become negative 5 over 4. This problem is one of those that's so easy it's difficult. You might be overthinking this. So the derivative of 10, this is just a horizontal line. The slope of this is just 0. To take the derivative of this function, I'm first going to rewrite these with negative exponents. So this is going to be 4x to the negative 1 minus 4x to the negative 2 plus 4x to the negative 3. Now that I've done this, I can use the power rule on each of these because this is just x to a constant at this point. So going from left to right, we've got negative 4 x to the, we're subtracting 1, making it more negative, so that'll be negative 2. Next, this is going to be positive 8 x to the negative 3. And finally, we have minus 12 x to the negative 4. For this free response problem, prior to a sporting event, the number of automobiles entered in the stadium parking lot is modeled by this function a, which is shown in the table here. And it's a differentiable function for whatever that's worth. Now, so according to the model, we want to know the average rate at which automobiles enter the parking lot. Automobiles per minute over the interval 45 to 90. So we're asking for a rock from 45 to 90. So basically we're going to do a of 90 minus a of 45 over 90 minus 45. So in this case, if we're doing that, that's going to be 450 minus 190. And what does that come out to? Well, this is going to be, let's see here, 215 over 45. We could reduce that if we wanted to. These are reducible by 5. 45, that reduces to 9. 215, well, let's see, 5 goes 40 times into 200. So this is going to be 43 over 9, and that is in automobiles per minute. For this part of the problem, they want us to write a prime, the derivative of a here, as the limit of a difference quotient, and then use the data in the table to approximate a prime of 95. Okay, so a prime of 95, the derivative, if you want to write that as the limit of a difference quotient, you're essentially asking for the IROC formula. So we want the limit as h approaches 0 of, and now we need our big fraction here. So normally we have f of x plus h minus f of x. Well, in this case, f function is really the a function. You're taking the derivative of the a function. So you're going to be doing a of, and you would normally have t plus h, but in this case, we're plugging 95 in here. So we're actually going to say a of 95 plus h. Minus, we would normally have f of x, which would be f of t, but again, you're plugging in 95, so now we're subtracting a of 95. And all that's going to be over h. So there's the difference quotient that they were asking for. Next, they wanted us to use our data here to approximate this value. So we're not actually going to take the limit per se. We're going to estimate this. Now, if you want to estimate an IROC, the best way to do it is with an AROC, an average rate of change. So we're going to find the average rate of change of an interval that 95 is on. In terms of getting the best approximation, we should probably make it the smallest interval possible. So the interval from 90 to 100 would work nicely for this. We're going to do then a of 100 minus a of 90 over 100 minus 90. So this is going to be 600 minus 405 over 100 minus 90. We can reduce this if we wanted to. You can simplify it. You don't have to, but you could. This is 195 over 10. And then those are both going to reduce by 5. So this is going to be, let's see here, 200 divided by 5 would be 40. So this is going to be 39 over 2. And there it is. Whoops, let's make that over 2, not over 5. All right, now we're good. For this part of the problem, we want to know the shortest time interval during which it is guaranteed that a of t equals 400 for some t in the interval. So that's the issue with these tables here, is there's not a whole lot of guarantees in terms of when you get what value, because we don't know what's going on in between these table entries. Pretty much anything could be happening. But they did give us a little bit of information. They said that this problem had a differentiable function a. And differentiable, if you haven't studied that yet, basically means that you can take the derivative, and that means a whole bunch of things, including that your function is continuous on the interval where it's also differentiable. So we're guaranteed that we have a continuous function on the interval from 0 to 100. That means that we're not allowed to skip values as we move between these different y values here. So that means that we're guaranteed that we're going to find 400 for an output somewhere in between this 250 and this 405, this 70 to 90 interval. We just have to justify it a little more rigorously. So the way we're going to do that is using the intermediate value theorem. We've already shown that we have continuity across all these intervals. We just needed 70 to 90, but we've got the whole thing, so that's good. We also have to show that the value we're looking for is sandwiched between the beginning and ending y values on the interval that we're using. So let's take a of 70, which is 250, and that should be a of 70. There we go. That's 250. We also know that a of 90 is 405. And since 400 is between 250 and 405, the intermediate value theorem guarantees there is some time on the interval from 70 to 90 for which a of t equals 400. On this last part of the problem, they're telling us that for times 0 to 45, our function is modeled by this function right here, this polynomial here. We want to find basically f prime of 10, which would tell us the number of parking lots entering per minute at time 10. All right, so let's go ahead and use the power rule on this. So this is going to be 4 over 27 times t to the 1 if I use the power rule on that first thing there. And then for this 8 over 9 t, that's just going to be 8/9. It's just the line rule being used. So f of 10, we just have to plug 10 in for t. So you could plug in 10 and call it a day and just move on. If you wanted to simplify this, though, this is 40 over 27 there. And we need a common denominator if we're going to combine this 8/9. So I'm going to rewrite this right away as 24 over 27 for a grand total of 64/27. And that's autos per minute.